Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Dr. Anirban Mondal. Anirban did his master's thesis at the Indian Institute of Technology, Bombay, under the supervision of Professors Deb Mady and Rodney A. Fernandez. His master's research was focused on directing group-assisted meta and para-CH functionalizations of arenes by template-based assemblies, as well as the total synthesis of the anti-tumor drug Quinolid. He recently completed his PhD in the group of Professor Ben Feringa, specializing in chemically driven molecular switches and motors, as well as asymmetric catalysis. Currently, he's working as a guest researcher in the same lab. And with that, I'll hand it over to you, Anirban. Thank you very much for joining us today.
Thank you, Matthew, for the kind introduction and the invitation to speak at this fantastic platform. I'm really inspired by the awesome work you are doing to bring exciting chemistry to the worldwide audience through your platform. Congratulations and all the best to you for the future. Today, I'd like to talk about the synthesis of chiral phosphines using an unexplored stereoselective CP cross-coupling reaction. In modern society, phosphorus compounds with a unique chirality due to the presence of a p stereocenter plays an important role, including in the use of agrochemicals for food supply, as a drug for the treatment of diseases, in the synthesis of high-performance materials, and especially as a chiral ligand in asymmetric catalysis. However, there are lack of methodology available for the synthesis of phosphorus compound in which the chirality at the phosphorus atom can be readily controlled during a carbon-phosphorus bond formation reaction. Therefore, the development of new methods to produce chiral phosphines are highly desirable in terms of current performance criteria, that is, sustainability, easy access to the starting materials, high tolerance to the functional groups, and excellent yield and stereoselectivity. Under current scenario, chiral phosphines is generally prepared when required through a stereospecific reduction of comparatively more stable chiral phosphine oxides. Therefore, the present research focuses mainly on the synthesis of p-chiral phosphine oxide or the phosphonate using an advantageous route. In general, there are currently three methods for obtaining those extremely important p-chiral phosphine compounds are available. The more traditional method, which involves the resolution of racemate, sincerely speaking, has serious drawbacks. For example, it requires tedious recrystallization and chromatographic separation that results in low yields to the desired optically active phosphine oxide. To address this intrinsic problem of chiral resolution, that led to the development of another viable synthetic route as shown in the middle, that uses a stoichiometric amount of a chiral auxiliary, which allowed the preparation of a suitable p-resolved precursor by reacting phosphonyl dichloride with the chiral auxiliary. From this precursor, via a stereoselective substitution reaction, a new CP bond were created that led to the desired phosphine oxide with much higher conversion as compared to the first method. Similarly, a metal-catalyzed alkylation or arylation of prochiral phosphine oxide or its derivatives having a pH bond is an effective method as well for producing p-stereogenic phosphine oxide. This method relies on the control of stereochemistry at the reacting phosphorus atom using an external chiral ligand. While it may look promising, those methods are still underdeveloped due to the poor control of stereochemistry, difficult access to the starting materials, and need for expensive chiral ligands. Moreover, a general traditional metal catalyzed method relying on the direct use of a phosphine 3 as a starting nucleophile for a PC cross-coupling reaction has been investigated extensively for some time, in addition to that has been shown before. The earliest work of Gruik and co-worker shows that they can induce enantiomer selectivity in a CP coupling of a secondary phosphine with phenyliodide in a palladium catalyzed process. However, as you can see, the level of enantiomer selectivity in such p-arylation processes is very low. The reason for this stereoselectivity issue associated with this method is that the initial and the final phosphorus compound compete against the chiral ligand to coordinate with the active catalyst, which erodes the enantiomer selectivity. To overcome this, a bulky substrate or more functionalized phosphine coupling partners are usually required that restricting the generality of this method. Therefore, it is highly desirable to develop alternative strategies for the synthesis of p-stereogenic phosphine compounds. To tackle this issue, we decided to use phosphoamidite as a starting material. The reason is phosphoamides are already well constructed to fulfill three basic functions required for achieving excellent stereo control. Number one, the presence of binyl chiral auxiliary for stereo induction, P center for annihilation, and they can also serve the purpose of a chiral ligand. Hence, no question on the competitive ligand binding. But before we dive into this exciting chemistry, let me give you a brief story about phosphoamides. Phosphoamides were first introduced by our group. As we can see here, the excellent enantioselective 1,4 addition of alkyl gene reagent to enone was observed in a copper catalyzed process in the presence of those binyl derived phosphoamidite ligand. This led to a breakthrough in asymmetric conjugate addition, and later they were used widely in other asymmetric reactions as well, including the 1,4 addition, asymmetric hydrogenation, asymmetric cross-coupling, CH activation, and many more. In case you would like to know more about phosphoamides, please do not forget to check out the review mentioned in the top corner of the slide. Since phosphoamides are mainly used as ligand in industry, we would like to have an idea to use them as starting reagent for asymmetric p-arrivation. The conversion from A to B can be achieved in a single step through a metal catalyzed CP cross-coupling reaction between a phosphoamide and an aryl halide or a triplet to generate a homochiral P center. The key to this success is the axial to central chirality transfer from binyl to the phosphorus atom during a catalytic cross-coupling event. This method replaces the use of an external chiral ligand. This is because the binyl containing phosphoamide already has the intrinsic properties of a chiral ligand that can simultaneously serve as a substrate. Let's dive into the proposed mechanism. We envisioned that in the first step, the formation of an aryl palladium-2 complex through the coordination of the phosphoamide A to palladium 0 and subsequent oxidative addition of an aryl halide takes place. Consequently, reductive elimination could then form a yet unexplored chiral phosphonium salt 3. In this step, oxidation of phosphorus 3 to phosphorus 5 has to occur, and at the same time formation of a new CP bond. The newly formed phosphonium Catal 3 would be electrophilic in nature at the phosphorus center and therefore could be attacked by water to form the hydroxyphosphorane intermediate 4. And this intermediate is highly unstable and would eventually be converted to the thermodynamically more stable product 5 by stereospecific cleavage of one of the PO bond of the binyl. This cleavage of the PO bond is an important factor in determining both the chemo and stereoselectivity of the process. Having proposed the mechanism on paper, we were eager to test its viability in our laboratory. Our initial experiments were a great success as shown in NT1, and a comprehensive reaction optimization reveals that the p-arrivation proceeds using a para-iodoanisole in the presence of palladium 2-DBA3 as catalyst, cesium carbonate as base, with quantitative conversion and excellent diastereoselectivity towards the CP coupled product 2AA as highlighted in green. It is also interesting to note that aryl bromides and triplets NT10 and 11 are also smoothly converted to 2AA. However, this required an elevated temperature of 100 degrees instead of 70 degrees in both cases. Also, the diastereomeric ratio was slightly reduced due to the higher temperature of the reaction. After having the optimized reaction condition in hand, the scope of aryl iodides was evaluated. Aryl iodides substituted with a range of electron donating and electron withdrawing groups reacted smoothly to furnish the corresponding p-chiral phosphoamides, with in most cases excellent yield and diastereoselectivity. A notable difference in reactivity was observed between 1 and 2-iodonaphthalene, as shown in the top corner, while phosphoamide 1A reacted readily with 2-iodonaphthalene to afford 2Ag in 86% isolated yield, and no conversion was observed under the same reaction condition when 1-iodonaphthalene was used. which we attributed to the increased steric hindrance present for this specific iodostatic material. The decreased reactivity of one iodonaphthalein can be readily compensated by switching to the phosphoamidite 1B instead of 1A, as observed in the formation of 2BD in 66% yield and excellent diastereoselectivity again. Aryl iodides substituted with various halogens were also tolerated, providing the corresponding products in good yield and high diastereoselectivity. However, it is remarkable that in the presence of both bromo and iodo-leaving group in the same electrophile, for example in the case of 2AK, only aryl iodide participated in the CP coupling event, leaving the aryl bromide part intact. This chemoselectivity provides an additional and versatile means for subsequent functionalization for the chiral product. Many functional groups were also tolerated, such as halides, phenols, alkenes, ketone, alkyne, ester, and both protected and unprotected aldehyde, providing products in good yields and excellent diastereoselectivity. In general, the aryl iodides containing an electron withdrawing groups reacted more slowly under the standard reaction condition, which is 70 degree, but increasing the temperature to 100 degree significantly enhanced the product yield without decreasing the diastereoselectivity. Finally, heteroaromatic iodides such as 6-iodoquinoline, 3-iodothiophene were successfully converted into the product. To evaluate the scalability of our methodology, the transformation was performed on a multi-gram scale, for example 5 gram in this case. After easy purification, the product 2AB was obtained in excellent geoselectivity. In all cases, the absolute configuration were based on the known configuration of the bienal moiety in the phosphoamidite and X-ray crystallographic analysis of 2AMA, as shown in the middle. In order to gain a deeper understanding of the mechanism of this highly selective aryl coupling, we examined the possible pathways to characterize the phosphonium intermediate, as shown in the right. Under standard reaction condition, we were unable to observe any other species except the hydrolyzed product 2AB, either before or after the aqueous workup, suggesting that the anticipated phosphonium intermediate formed in the palladium catalyzed coupling process with phenyl iodide is highly susceptible to hydrolysis by trace amount of water. As a solution, we decided to perform a reaction in the presence of potassium triplet as the additive in order to stabilize the phosphonium salt formed in situ. And that can be possible by exchanging the iodo anion with the triplet anion. With regard to the stability of the phosphonium triplet, we will come back to that later with a better explanation. Indeed, a full conversion of the phosphoamidite 1A was observed according to the 31P crude NMR. Also, we observed the formation of a new species at 55.4 ppm in the 31P crude NMR, suggesting the formation of the phosphonium triplet, alongside substantial amount of the hydrolyzed product 2AB. The observation of the hydrolyzed product 2AB indicates that the anion exchange and the hydrolysis are a competing reaction. With this exciting result, we performed a parallel experiment in which we decided to perform an independent synthesis of the postulated phosphonium triplet intermediate using diphenyliodonium triplet instead of phenyl iodide as the electrophile. This avoided another exchange reaction between an iodide and the triplet. Indeed, a complete conversion to the phosphonium triplet was observed, and after further purification steps, the structure of the phosphonium triplet was determined using NMR spectroscopy, high-resolution mass spectroscopy, X-ray single crystal analysis, and 2D NMR analysis. Later, the subsequent water addition step was tested, which indeed converted the corresponding phosphonium triplet to the phosphoamidate CP coupling product. And this finding supports the hypothesis that the quaternary phosphonium salt is the key intermediate during the palladium catalyzed arylation process, and that both aryl coupling and the water addition step occur with excellent stereo control at the phosphorus center. Now one might wonder how chiral phosphonium is more stable when triplet is a counter anion instead of an usual iodide ion. A possible explanation on the higher stability observed for the phosphonium triplet compared to the iodide could be formulated by having a closer look at the crystal packing and the nature of the possible interaction between the cations and anions. As clearly visible in the zoomed-in structure, the pair of phosphonium cations are associated through a series of hydrogen bonding interactions with the triplet anion. In contrast, in the case of phosphonium iodide, those hydrogen bonding interaction between an iodide anion and the corresponding phosphonium cation will not be possible, and therefore they are more susceptible to hydrolysis. And that is the reason we are unable to observe those intermediates. In the last few slides, I will try to show you how we can make use of this excellent stereoselective arylation product to prepare various useful p-chirogenic compounds, such as hard-to-access p-chiral phosphinates and phosphine oxide using a downstream chemistry involving various nucleophilic substitution at the phosphorus center. To achieve this, we chemoselectively exchange the amino groups with the methoxy groups, which provides a better nucleophilic leaving group for the organometallic reagents we thought of using. To avoid deprotonation, we also protected the phenyl wedge group with a wide range of protecting group. Unfortunately, the nucleophilic substitution reaction wasn't as straightforward as we might have thought. The synthesis of the desired product 5A resulted in a considerable amount of byproduct 6A and loss of enantioselectivity. However, we were able to achieve excellent selectivity against the homochiral phosphonate 5A by a mono addition process by optimizing both the solvents and the protective group present in the bienol. It is interesting to note that the protecting group that is present in the bienol plays a significant role in both enantioselectivity for the formation of the product 5A as well as the formation of the byproduct 6A. Having obtained the optimized reaction condition, a small scope was achieved for the synthesis of various p-chiral phosphinates precursor. We utilized those phosphinates to synthesize many other tertiary phosphine oxide by using many Grignard and lithium reagents. Therefore, we are confident that using our methodology, a variety of functional groups can be introduced at different stages of the reaction according to their tolerance and availability in order to prepare a diverse range of homochiral phosphines. The enantio-divergent nature of this reaction is another significant characteristic of our protocol, as shown in this slide. For example, each enantiomer of chiral phosphine oxide 7AB can be generated from single 4C starting material with an excellent enantioselectivity by just altering the addition of the reagent, without caring about the chirality present in the bienol as well as at the P center. As regards to asymmetric catalysis, one of the most important steps of our protocol is the synthesis of p-chiral phosphine in the oxidation state of 3, and also used as a valuable ligand in asymmetric catalysis. Therefore, we demonstrated that the tertiary phosphine oxide can be readily reduced to the corresponding boron complex without affecting its stereochemistry. Next, we were also curious about the mechanism of the stereospecific nucleophilic substitution at the phosphorus center, particularly the role of the protecting group in determining both the ratio of 5A and 6A and enantioselectivity of 5A. As you can see at the right corner of the table, which shows that different protecting groups have different outcome of the stereoselective substitution reaction. And this might be answered by looking at the mechanism shown here. As you can see in the proposed mechanism, the reaction can proceed according to two different pathways. Pathway 2 indicates a first addition-elimination reaction that generates 5A as a stable intermediate that can react further to form 6A. This means that the bienol leaving group should have only minimum influence under this route, which does not appear to be the case according to the table shown in the right corner. Hence, we hypothesize that the pathway 1 would be the most possible pathway to form 5A and 6A through the formation of a pentacoordinated species A after the first Grignard addition step. Intermediate A can be easily hydrolyzed to generate 5A or undergo a second Grignard attack to form an intermediate B, which upon hydrolysis forms the achiral phosphine oxide byproduct 6A. Thus, we believe that the protective groups in the biennial leaving group plays an important role in the formation of both 5A and 6A by modulating the steric and electronic properties of the pentacoordinated species A. In conclusion, homochiral stereogenic phosphorus compounds are obtained through an excellent palladium-catalyzed asymmetric CP coupling process involving aryl halides and phosphoamides. The isolation of the key intermediate revealed the axial to center chirality transfer involving stereoselective formation of a unique chiral phosphonium salt. The protocol uses readily available reagents and simple condition and provides a flexible platform for the construction of broad array of P-chiral compounds with a downstream chemistry shown here in this slide. In all the steps, configuration at the phosphorus center was characterized through X-ray analysis. I also recommend to check out the following highlights of this work to get an instant summary of this work. With that, I would also like to thank my colleagues, Nicholas, Ruth, and my PhD supervisor, Professor Feringa, for their enormous contribution that made this work possible. And I also would like to thank you for your kind attention. Thank you very much.
Thank you for joining us for this Research Spotlight episode, and thank you to Anirban for a very interesting talk. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.